Tap water kills more than 100. A century-old college tradition turns tragic. American tanks turn out to be death traps. 14 die when a building under construction self-destructs. And the Great Airport Luggage Massacre. Now, engineering disasters on Modern Marvels. Tap water. As it flows from spigots in our kitchens and bathrooms, we expect it to be safe to drink. We trust treatment plants to remove any harmful impurities that might work their way into the system. But in March 1993, hundreds of thousands of Milwaukee residents became ill from drinking their household water. Grocers sold out of bottled H2O, and Milwaukeeans anxiously lined up to receive purified water.
One local health official in early April described the situation in Milwaukee as a near panic because so many people were going to their doctors, so many people were showing up at emergency rooms and hospitals with intestinal illnesses.
We'd all been asked, something going on, my neighbor's sick, my child's sick, and we actually, as we began to look around, we noticed a number of coworkers weren't around, and that's kind of a flag to us that in fact it's more than just a flu, there may be something actually happening.
Within 2 months, 100 died, and more than 400,000 suffered illnesses ranging from diarrhea to fever to vomiting.
I think it's important for people to take that precaution and boil water, and either for drinking or for washing food.
Investigators discovered the majority of suffering residents were receiving water from the Howard Avenue treatment plant, one of 2 facilities serving 800,000 Milwaukee citizens. The Howard plant treated more than 100 million gallons of water per day. Its main supply intake was located 3.5 miles away in Lake Michigan. Was there indeed something in the water causing the problem?
The first week of April, a physician tested specimen from a patient for a specific parasite, the protozoan Cryptosporidium, and found it, contacted other physicians and health officials. They tested other samples, confirmed that it was Cryptosporidium.
Cryptosporidium, shown here, is a microscopic parasite, more commonly found in animals than human beings.
It's a one-celled creature. It multiplies in the intestines of infected humans or animals. It comes out of those intestines in the feces, comes out in a little egg-like packet called an oocyst, and that's the infectious stage for the next person who ingests it.
Tests of water samples from the Howard Avenue plant showed the presence of Cryptosporidium. The parasites may have entered the water as the result of several factors.
And those things that I think about as occurring were heavy rains falling on icy ground, so there's a lot of water runoff into rivers, creating a lot of muddy water. Also potentially bringing in Cryptosporidium oocyst, the infectious stage of Cryptosporidium, into those waters. Then that water being taken into a water treatment plant that wasn't filtering their water in an optimal way.
Filters at Milwaukee's Howard Avenue treatment plant, like those in most of the U.S., were made up of layers of fine-grained sand, designed to catch any foreign substance. Milwaukee health officials acknowledged that the sand had not been maintained properly.
Filter beds needed to be cleaned. They could have been cleaned more often. There are turbidity monitors and sensors that could have been placed in more spots along the process, so you would have had more continuous monitoring of the water quality. We had more of an intermittent monitoring of the water quality.
You need to think of a water treatment plant filter more like a bucket with holes punched in the bottom full of sand. This bucket happens to be a 20-foot by 20-foot pool, but it's the same principle. And no matter how tightly you pack those little grains of sand, there's still microscopic holes in those grains of sand. And those holes are much bigger than the oocyst.
In order for sand filters to work properly, water must first be treated with chemicals to make the tiniest impurities bond with others, to form particles large enough to be caught by the filtration system. This bonding process was not working sufficiently in Milwaukee, allowing cryptosporidium to slip through the cracks.
There were upgrades to the plant that could have been made that hadn't. Milwaukee was very proud of its water. We'd been making products from water. We'd been drinking clean water out of Lake Michigan for well over 100 years. And in retrospect, I think we were a little complacent that those improvements hadn't been made. There was no reason to make them. There was nothing to believe that anything was wrong.
Once cryptosporidium was determined to be the cause of the problem, then came the tougher question: how to get rid of it. Just as the process for cryptosporidium to enter the system was highly complex, so was the fix.
They made a lot of changes in their whole operation. Number one, they did correct the coagulation pre-treatment process, so they got the turbidity down where it should have been. Number two, they invested a lot of dollars in a new chemical treatment process that would kill oocysts, called ozonization. Ozone is a much more powerful disinfectant than chlorine is, but it's very expensive to produce. And the third major change they made is changing the location of their water intake. Prior to the outbreak, the water intake was close to where the rivers and sewage plant discharged their waters, and they were drawing some of that water back in that intake. They now moved that intake quite a ways away from that.
The Center for Great Lakes Studies and the Great Lakes Research Facility, which is behind us here on the Inner Harbor, they participated in a study that indicated that if they extended that water intake pipe less than a mile, just 0.8 of a mile more out into the lake, they would avoid 98% or more of the possible pollutants that would be flowing along the near shoreline. So that moved them out of that plume of contaminants that regularly flow along the shoreline. So that also helped avoid another outbreak in some future spring.
When the fix was complete in Milwaukee, the Howard Water Treatment Plant became one of the most advanced in the nation. But the solution came at great cost, both in lives and dollars.
There's been a lot of debate whether or not the people of Milwaukee needed to spend $80 million to convert their water treatment plants to the ozone process. But given the intensity of this outbreak, the number of people that were affected, the deaths that we mentioned, the people of this town really demanded that the water treatment plants in Milwaukee be upgraded to the best of their ability, and we're willing to spend the $80 million to do so.
The delicate balance between risk and expense will always be a source of controversy. But Milwaukee public health officials are confident they've made the right decision. They know the alternative.
People ask me this all the time, will it ever happen again? Could it ever happen again? Well, the ozonation process that we've installed makes it very unlikely, but I still have enough public health and science in me to say you never say never.
The Milwaukee water treatment disaster made many American cities examine and upgrade their own methods of filtration. Few have gone to the trouble and expense of a total system overhaul like that of Milwaukee. But there is no doubt that the quality of tap water across the nation has improved as the result of one city's tragic engineering disaster. Boiling tap water for at least 1 minute kills cryptosporidium parasites. Engineering disasters will return on Modern Marvels. Texas A&M University in College Station, Texas, is a school of honorable tradition. Once an all-male military school, the now co-ed campus still reflects a history based on discipline, motivation, and pride. One of the most popular and long-standing traditions has been the elaborate building and torching of a giant bonfire the night before Texas A&M plays football against arch-rival University of Texas. A tradition which turned tragic in 1999 with a collapse during bonfire construction. resulting in the deaths of 12 students. The disaster brought an end to the annual Aggie bonfire, the first of which burned in 1909 as a pile of rubble.
You can look at the pictures from year to year of the bonfire and see where it grew not only in size and shape, but it was also made of different materials. Starting with the trash, then they switched to lumber, which was originally cut off the university and then cut off of private land. And actually one of the evolutions that occurred in the whole bonfire activity was that the building of the stack became a minor part of the entire Aggie bonfire experience. The actual cutting of the wood was a more involved activity.
By the time Jim McTasney became head Red Pot, or bonfire organizer, in 1992, students hand-cut logs at nearby forests needing to be cleared, trucked them to the campus bonfire site, then spent weeks lashing the logs together with steel wire, slowly filling out a stack built around a center pole supported by guide ropes. As many as 3,000 students worked on building the stack.
The purpose of Aggie bonfire to the students that built it was not to build a stack.
Provide answers to why this tragedy occurred.
It was to go out there and experience leadership. And in order for Aggie bonfire to be the valuable leadership experience that it was, and the valuable training ground that it was, you had to keep the physical labor in it. You purposefully shunned the mechanization and the automation in order to allow as many students as possible to participate.
According to tradition, if the bonfire burned past midnight, the Aggies would win the game against the University of Texas. So emphasis in building the stack was placed not so much on height as its aesthetic appeal and ability to burn into the wee hours of the morning. Larry Gross, a professor at Texas A&M from 1981 through 1996, used his construction management background to help students design a structure that could look good and burn long.
I did go out and observe the bonfire and the lighting of it, and also the collapse of it after it is ignited. And we noticed how the rotation, it did rotate as it came down. To eliminate that rotation action, we suggested to interlock by having the logs from the top layer extend into the lower layer, space them throughout, and this would help to lock the two stacks together, and this would eliminate that rotation action.
Larry and Red Pot student organizers analyzed other structural issues as well.
We suggested that they move out from the center pole maybe 20 or 25 feet and drill a series of holes all the way around the bonfire and set the poles into the ground, and this would help to stabilize that bottom layer of them. And then we would fill it and take a cable and cinch it up. And by doing that, it really made a good structural and strong bonfire then.
Larry Gross viewed building the bonfire as a valuable educational process. So much so that bonfire design became an independent study class.
Here were a number of young students who had an issue of, obviously, a budget issue they had to follow. They had a schedule. It had to be ready to burn the night before the football game. They had to be safe. So it had all the makings of a major construction project. And the class project was to develop a procedures manual for constructing a bonfire.
Photos of bonfires during this time period suggest the obvious attention to structural detail. But then came November 18th, 1999. Students worked throughout the night to build the bonfire, scheduled to burn a week later. At 2 a.m., as cranes lifted logs to those working on the top and the sides of the stack, the unimaginable happened. The entire structure collapsed. result was tragic. Despite the efforts of rescue workers to remove the heavy logs as quickly as possible, 12 students were found dead. 27 were injured. Following 90 years of successful Aggie bonfire building, what went wrong? Texas A&M established a commission to determine the answer. According to the commission report, the collapse occurred for several reasons. As comparisons with earlier bonfire stacks reveal, a decision had been made in 1999 to try to make the tiers more straight up, vertical, as opposed to earlier teepee-like shapes, in which the logs leaned slightly inward. The logs used in 1999 appeared to be more irregularly shaped than those used in previous years, providing a looser stack, harder to contain. Aggressive wedging of logs on the second tier to fill gaps below increased pressure on steel wire encircling the stacks, causing it to snap under pressure. Using the analogy of a wooden barrel, the hoop strength was not sufficient.
Some of the issues that we had developed with our students and with other faculty, not just myself, but other faculty in our department were involved with this. Apparently some of these activities were not being followed.
The commission's report concluded that the tragedy resulted from a lack of engineering supervision. Surprising to many in view of how the structure increased in size and complexity over the years. The Aggie bonfire had always been a project run by students for the students. Larry Gross's involvement had been considered a casual, informal student-teacher collaboration.
The collapse was about physical failures driven by organizational failures whose origins spanned decades of administrations, faculty, and students. No single factor can explain the collapse, just as no single change will ensure that a tragedy like this never happens again.
1999 was the last year the bonfire was built. Today, a memorial honoring the students killed in the collapse is being built where the bonfire once burned. It is unlikely there will ever be another Aggie bonfire. For student red pots like Jim McTasney, that's a major loss.
Any success that I have today, I can trace back to my experience with Aggie Bonfire. It was the most rewarding and educational leadership experience that I had at this university and have had since.
Aggie bonfires in the 1990s contained between 5,000 to 7,000 logs that were 8 to 24 inches in diameter. Engineering disasters will return on Modern Marvels. How many times have you seen images like this from film shot during World War II? Powerful American Sherman tanks rolling across the European countryside, delivering firepower to Allied ground troops where it was needed most.
The Sherman Tanks weight class was somewhere between a light tank, which was small, and a heavy tank was a big monster. It was designed to go over military bridges. It was designed to fit on railroad cars. It was designed for easy transportation. It was designed for automotive reliability.
When the decision was made to invade Europe, General George S. Patton himself selected the Sherman as his tank of choice.
He said, we don't need a heavy tank. We can win the war with this medium tank. Make as many of those as you can.
Sherman tanks rolled off American assembly lines by the thousands, nearly 50,000 total. When they reached Europe, 3 to 5 man tank crews immediately took them into battle. The image of the approaching Shermans became a myth-like representation of the invincibility of America's war machine. But But those who actually fought in and maintained the Sherman tanks claimed the invincibility was a myth. And as far as their design for World War II was concerned, the tanks were engineering disasters.
General Patton was quite a historian. He knew a lot about wars and the history of wars. He honestly believed that light tanks that were fast and mobile and could cut in behind the enemy, the tanks were not supposed to fight tanks. Now that is a very unrealistic view. You cannot put a tank in the field without preparing it to defend itself and to be able to fight other tanks. So he was basically off base there.
Belton Cooper served as a captain on a Sherman tank maintenance unit in the American 3rd Armored Division. He recounted his experiences in a book titled Death Traps. Cooper vividly remembers the first time he approached a disabled Sherman tank.
I was devastated. The first shot had gone through the transmission, and in addition to the 4 inches of armor in the transmission, it had gone through a 5-inch steel drive shaft, and that stopped the tank. The second shot hit the top of the turret and cut a 3-inch groove through about 3 inches of armor, and the blast killed the tank gunner. When I saw that, I thought this tank had a protection hole. And then after that, they started bringing tanks in droves with the dead and wounded inside, and it was just terrible. And I knew then that we had an inferior tank.
We had short-barreled guns designed to shoot high explosive shells at a fairly low speed, 2,000 feet a second. The German guns would shoot a solid shot at 3,500 feet per second. That meant that they had 2-3 times the penetrating power of our armor-piercing shells. And so they went through our tanks like a hot knife through butter.
The Shermans may have had the speed and mobility so highly regarded by Patton, but those were not the qualities needed to fight the larger German Tiger and Panther tanks. The statistics from Belton Cooper's unit speak for themselves.
We lost 648 tanks totally destroyed in combat, another 700 knocked out and repaired and put back in action. That's 1,348 tanks knocked out in combat. So that's 580% loss. So I don't think anybody took that kind of loss in the war. Army, Navy, Air Force, submarines, nothing like that.
In one unit, they sent 18 of these newly crewed tanks into combat, and in the first 20 minutes, 17 of them were lost. It was murder. It really was almost criminal what our forces had to put up with because we didn't have the right tanks.
Why were the Shermans so vulnerable? For starters, their offensive power was hindered by inadequate weaponry.
I have a letter in my file that came from General Eisenhower, and he wrote directly to General Rose, and he said, General Rose, I know you've been losing a lot of tanks. I'd like to have you ask your crew and your tank commanders and your combat commanders why we're losing so many Sherman tanks. And the best answer he gave was by a tank gunner who said, General, in order to knock out a German tank, I've got to get within 600 yards and catch it on the flank. They can knock me out at 2,000 yards head on.
For all practical purposes, a Sherman could successfully battle a German tank from just one direction.
The only way our tanks could defeat their tanks is if we could run around behind them and shoot them in the rear end where there wasn't much armor. We did that, but typically it would take 5 tanks being blown up before the 6th one got around to shoot a German tank at the back. The mathematics were not good.
When it became clear to American tank commanders that their magnificent war machines were so vulnerable, they resorted to makeshift methods that would add defensive capabilities and length to their lives.
Anything that they could gather, that they could put on that faceplate to protect it, they even put logs, they put steel plates. They put chicken wire backed up with 4 inches of concrete on the faceplate. Anything they could get on that to give them a thread of survival.
But for the most part, any effort to improve the Shermans was futile. To make matters worse, Shermans required highly flammable, high-octane gasoline. Their engines were originally designed for airplanes.
In every decision that was made in the development and use of the Sherman, from beginning to end, they had to make choices between options. Okay, we need a high-powered engine with lightweight. Okay, we use this engine. It's an aviation engine. It burns more flammable fuel, but power is the most important thing, power and weight. Or we need a tank that can move very fast to exploit a breakthrough. So we can't have real heavy armor because that would slow it down. We'll have just enough armor for what we think we need.
The job of a Sherman tank maintenance engineer was a grisly one.
We had to clean the tanks out. It's a terrible job to clean out a tank with the head shot off and the arms and legs dismembered. It's just awful. And we had to put the men inside the tanks to get the bodies out and wrap them up in a tarp, and then we'd put them on the side. And the tank crews knew that when they got in that tank and went to battle, if they got hit, they were going to be in bad shape.
For soldiers like Belton Cooper, whose World War II duties involved tank maintenance, there is no doubt who the unsung heroes of World War II are. The crews of Sherman tanks.
Their tanks were knocked out and sent back to repair, and then they came back and they got into a tank that had just been freshly painted to cover over the blood stains, that had obvious patches in it from where the mechanics had plugged the holes. They knew what they were going up against, and then they went out and did it again. It was the most heroic thing I can imagine, because they knew they were outclassed. They knew that if they ran up against a Tiger or a Panther tank, they were in a lot of trouble. And they still got in those tanks every day, and they went out and beat Germany.
Sherman tanks, remembered by their designers for speed and agility, and by their crews for being the right tanks for the wrong war.
We were just inadequate. That's all I can say. We just did not understand what we were doing. It's a great tragedy.
The Sherman tank was named after Civil War Union General William Tecumseh Sherman. Engineering disasters will return on Modern Marvels. 40 miles outside the city of Denver, Colorado, stands what appears to be a sculpture of modern art. With its tent-like white peaks glistening in the sun, DIA, Denver International Airport, was designed to represent the perfect combination of aesthetic form and practical function. A state-of-the-art airport for the entire world to emulate. DIA's designers wanted to impress not only with architectural innovation, but with an advancement in technology that had never been attempted. A computerized, totally automated baggage transfer system that would move luggage from curbside to plane to plane, and plane back to baggage claim with unimaginable speed and efficiency.
The hope was that they would have a way to almost instantaneously move the bags from one aircraft to another inexpensively, without people, and very reliably.
On March 10th, 1994, airport supervisors were ready to show the system to the world.
This is the world's largest, fastest, most sophisticated baggage system. It utilizes over 3,100 cars running on 20 miles of track. It's powered by over 10,000 motors, 100 computers, and the whole thing is interconnected with 14 million feet of wire.
There was only one problem. The system wasn't ready to be seen.
It was a public relations and operational disaster. There's just no other words for it. The images that appeared in the papers at the time were of bags being chewed up, being open, thrown on the floor. It was a mess. The pictures weren't staged. That's what really happened when they opened it. They weren't ready for prime time when they invited the press in.
The news media had a field day with the first display of the baggage system of the future. DIA, as in baggage, dead in arrival, became a popular phrase. Other terms used were the luggage eater, the DIA debacle, and the greatest thing to happen to the carry-on baggage industry since wheels.
I share your frustration that this magnificent new facility is not yet open.
Because the system had been designed with no backup, the opening of the airport of the future was delayed into the future by nearly a full year. The estimated loss of revenue was $1 million a day, all because of an engineering disaster.
Are we all ready? We're all ready. All right. 3, 2, 1. There we go.
When DIA finally did open, the automated system had been relegated to backing up a more traditional system. Man takes bag off plane. Man puts bag on conveyor belt. Man takes bag off conveyor belt. How could the creators of such a masterpiece of artistic design have produced such an engineering disaster? In order to answer that question, it's important to see this. A masterpiece of engineering and computer technology. Whizzing luggage along an incredible labyrinth of belts and tracks underground at DIA is in effect how the system was supposed to work, which happens to be how it's finally working now. At least for United Airlines flights. It's taken 10 years to solve the problems airport authorities originally hoped could be resolved in 2. So what happened? Why wasn't it ready?
I guess in some ways the major problem with the system was hubris. That is, people thought they could do it and they didn't have to deal with the reality. But in terms of the technical things that happened, it was a whole range of issues.
The DIA automated system was designed so that every bag would be carried to its destination by an individual telecar. A bag begins its trip through the system by having a barcode on its ID tag, read by a laser device. At the time the airport opened, barcode readers were the single line variety, incapable of obtaining a read with one quick swipe. Bags were sent to the wrong planes or to no man's land. Today, conveyor belts deliver luggage through cobwebs of advanced laser beams that read barcode tags without the bag even slowing down.
The technology has grown so much that these now, I don't know if you see it, but it's sort of a spider web where it's on a holographic disc, and the diodes that read the barcode, there's 6 of these, and that gives it so much more opportunity to read the barcode.
The bag is then automatically placed in a telecar. Destination information read from the barcode is transferred to the car, so it knows what path to follow. Like taxis waiting for passengers on incoming flights, empty telecars are always ready to jump onto the system to handle heavy traffic. At the system startup, the ability to handle heavy loads of baggage in peak travel periods just wasn't possible with the automated system. Today, it's no problem. Extra-large telecars take care of oversized baggage, like golf clubs and skis. Computers in a central control facility track the location of every telecar as it makes its way through a 17-mile maze of intersecting track. Accurate tracking was a major flaw in the original system. mainly caused by computer software, ill-equipped for the task.
I can tell where the bag is in the system. I can tell what the passenger that bag belongs to, where the bag was input into the system, the city that it's destined for, the makeup unit, the time the flight leaves.
On their routes to and from planes, all baggage cars need to take a dive below runways into what engineers now call the hellhole. When the system was first put into operation, gravity took control at this point, allowing many bags to tumble off the track into the jaws of luggage-chopping machinery. Today, telecar speed is controlled by in-track magnets, which slow the descent.
But by the use of these reverse magnets, we were able to slow that car down so none of these bags fall out of the car while it's traveling down the hellhole. Right now, we're probably cranking anywhere between 10 to 12 miles an hour. By the time we finish down there, we're anywhere between 3 to 5.
Should any bag, for whatever reason, fall out of its car, detection devices using RF, radio frequency technology, immediately halt the system and inform operators in the central control center, so the escapee can be captured and set on the right path. This form of RF tech was not available when the airport opened and has brought with it a whole new level of dependable speed to the system.
It's a workable piece of engineering and marvel. I've been amazed by it since the opening of the airport that I've been here. The system can go anywhere from probably 1750 to about 2,300 feet per minute, which still beats almost every conveyor system out there right now. It's very quick.
Finally, each bag ends its automated thrill ride in a holding makeup area where low tech takes over. Human beings place the bags on old-fashioned trams to be loaded onto planes.
With all the wide bodies, we probably see about 1,500 bags a day. So that would probably be the end of the journey for the bag from its location in the terminal to out here.
Although the automated DIA system is now working as it should have been 10 years ago, a backup system is in place. People-driven trams have their own concrete highway underneath the flying automated system to carry bags if the system goes down, or when flight delays require hot transfers, fewer than 15 minutes between connections. Simply put, the DIA baggage system became an engineering disaster for one reason. Too much was expected too fast. Today, even though the automated system is alive and well at DIA, it is only being used by United Airlines, which uses Denver as a major hub. That means computerized baggage handling, though working successfully, is handling only half the load for which it was originally intended. Since DIA installed the system, no new airport in the world has attempted to duplicate such a massive undertaking. The biggest problem for DIA's automated baggage system continues to be wheeled suitcases, which tend to slip and slide on the high-speed conveyors. Engineering disasters will return on Modern Marvels. In Fairfax County, Virginia, the 26-story Skyline Plaza has been a popular apartment complex for more than 3 decades. During its construction, however, a tragic engineering disaster occurred that provided warning signals to an industry that thrived on building the tallest buildings in the shortest time. It happened on March 2nd, 1973. Construction workers were pouring the concrete floor slab. One of 4 structures making up the tower collapsed all the way